Hi everyone, my name is Timothy Mucha, and today I'm going to talk about uncertainty quantification of wall-modeled LES of separating flows. And this is something I'm working together with Saleh Reza Ravesh and Philip Schlatter, and all of us are at KTH in Stockholm. So first a slide to set the background, discuss a little bit what wall modeling is. So the overall idea of wall modeling is to bypass the resolution of the inner layers of turbulent boundary layers, and therefore save a lot of computational resources when we conduct our LES. Now, there are several ways of doing it, but here we're going to use a technique called wall stress modeling. And the idea is that at each time step, we want our wall model to produce this wall shear stress based on the values of the unknowns somewhere a bit away from the wall, which are, of course, the velocity and the pressure. And all the quantities here are filtered. I simply assume the filtering operation. So usually these type of wall models are based on some kind of simplified Rance equation, such as equation 1 here on the slide. And now one can simply ignore the whole right-hand side, and which leads to a so-called equilibrium wall model. Typically these are coupled with some kind of mixing link type of model for the new t here, which leads to a logarithmic velocity profile once we integrate the ODE. Now this works well for the zero pressure gradient boundary layer case, but perhaps not otherwise. Now another idea is to ignore the acceleration term, but keep the pressure gradient term. And here we can also use the fact that, or rather an assumption, that the pressure does not change that much in the wall normal direction near the wall, so we can simply sample this guy from the LES. Now this has been used in quite a bit of works, but is also met with criticism, and the idea behind the criticism is that actually these two terms cancel each other out quite a lot. Which means that if you only take one of them and ignore the other, you might get a significant overestimation of the right-hand side. So the long-term goal for us here is accurate wall-modeled LES of separating flows, and to that end we want to develop wall modeling approaches suitable for non-equilibrium conditions, understand grid resolution and numerical requirements necessary for accurate simulation, and we want to do this in general purpose open source solvers, and in particular we're going to focus on OpenFOAM and NEC 5000. So one has to start somewhere, and we decided to start with a well-known case, a well-studied benchmark, which is a periodic hill flow. Have an overview here on the slide. In particular, we're going to consider the Reynolds number 37,000 based on the height of the hill, because for this is the highest number for which we have reference data, which is an LES by Glorfield and Chanella from 2019. So this whole study is going to be conducted in OpenFOAM using the built-in PimpleFoam solver. Among the numerical settings, I would like to highlight the LUS scheme, which is used for the convective term. This is a blend between a second-order upwind scheme and linear interpolation. We wanted to also conduct simulations in NEC 5000, but unfortunately, right now, we still haven't developed the wall modeling functionality to the extent where we can apply it to this flow. So this is something which we're going to do hopefully in the near future. In all the simulations, we're going to use the Whale subgrid model. I'm going to present results from two studies. The first one focuses on the choice of the wall model. Then we fix the grid to something which has been used in the previous study by Temmerman in 2003. It's a relatively coarse grid, as you can see here. I'm going to test three models: the equilibrium ODE model, the pressure gradient ODE model, and just not using a model at all. Now the second study is going to focus on the wall parallel grid resolution, and we're going to test 4 different values of number of nodes in the streamwise direction and X, and Z, which is also 4 choices corresponding to the spanwise direction. And Y is going to be fixed to 60, which is close to what Temmerman used. Okay, so the wall model study first. So we're going to look at the skin friction coefficient here, and on the bottom wall, of course, which is the most interesting one. So here we see that actually using the pressure gradient ODE model gives pretty good results on the majority of wall. Some difficulties here in the first third maybe, but nevertheless, I would say very nice agreement. Unfortunately, if we look at the equilibrium model, we don't get good agreement, and in fact, we see very little difference compared to just not using a wall model. And the reason for that is that actually the Y plus values on the wall, even with this rather coarse resolution, the wall normal direction, are pretty low. So I think the peak values are maybe around 30, which is then located here on this side of the hill. And it's here that we see that there's some difference between the predictions between the not using a wall model and the equilibrium model. Otherwise, the Y plus values are so low that the model basically thinks that we are still in the viscous sublayer, or maybe in the beginning of buffer layer. So it's almost inactive. So this highlights the need for higher Reynolds number benchmark data. Okay, so now looking at the grid resolution study, where we'll also focus on CF due to lack of time to look at more quantities. So here I just plotted all the curves from all the 16 simulations, and I colored them by the resolution of the streamwise direction. And basically the main conclusion here is that the results are actually really similar to each other, and there's not a lot of variation, not a lot of sensitivity to the grid resolution, which was a big surprise. I expected to have a much larger sensitivity, in particular to the resolution in the streamwise direction. This has been reported previously, but this is what we got. Some differences here at the peaks, but not a lot of difference otherwise. If we look at the mean velocity profiles, it's the same thing, very, very close profiles when you compare all the meshes. Now we're going to focus in a bit more detail here on the separation point and the reattachment point. So here I have a plot where we have an x and an z on the two axes, and the red dots correspond to the locations where we have the simulations. And the idea is we want to plot the distribution of error across the whole range of considered resolutions. And to build this kind of surface, this counterplot, we can use a technique called polynomial chaos expansion, which builds an accurate surrogate or an interpolant, whatever you want to call it. It's a very interesting technique. If you want to know more about it, I suggest you contact the co-author, Saleh Reza-Ravesh. He's an expert on these type of methods. Now, what we see here for the separation point is that for some reason using the values which are low, so low resolution, gives a better result. Now, this might be some kind of, just fortuitous cancellation of errors, probably. We have to dig deeper in order to understand this. Once you have this surface, a nice thing, you can also analyze the variance of the error and see what parameters contribute more to the variance, and this can be quantified in terms of these total Sobel indices, and you get an index for each parameter, and the higher the index, basically the more influence it has on the variance. So in this case, we see that NZ has a larger index. And this is well reflected in the plot. We see that changing x doesn't change the result as much as changing z. So this is all expected, but this is a nice way of putting a number to something one sees in plots. So now if we look instead at the reattachment point, we have a slightly different result. So first of all, we see that the response surface is split into these kind of quadrants. And this means that we're going to have approximately the same sensitivity to both parameters as reflected in the Sobel indices here. Both have very similar values. In terms of magnitude of error, it's lower than what we saw for the separation point. So it's within the bound, I would say, to -5 to +6, something like that. Now, for some reason, same thing here, that the best results are obtained for the coarse resolutions. So yeah, this is quite a surprise, and I would say, the biggest surprise I would say is that the results are so similar across the resolutions, and that using coarser meshes gives better results is also quite surprising. So in conclusion, we saw that the pressure gradient ODE model works well and does a good job of predicting tau wall. On the other hand, the equilibrium model does not do a good job because it's more or less inactive, even on the coarse mesh which we're using. And very surprisingly small sensitivity to the wall parallel mesh resolution. So this is something we're going to have to dig deeper into, and a lot of things to understand and discover here. So the next step is going to be also to try and consider varying the wall normal resolution, see if we get results which are sensitive to that. We expect that, it has to be. Now, we also want to try structured meshing strategies because this flow is actually well suited for that. Also, we want to look at more different types of wall models. Of course, there have been some developments which could be interesting, and naturally also extract more quantities, not just mean profiles, but look at spectral content, for example, in the detached shear layer, and see if we're actually resolving the necessary scales. Okay, thank you very much for listening, and I welcome comments and questions.